All right, today we're going to crack open a single scientific paper from 1905. And this thing, it didn't just solve a little puzzle. No, it completely rewired our understanding of reality itself. And the craziest part, it wasn't written by some celebrated professor in a fancy lab, but by a 26-year-old patent clerk.
So, picture this. It's 1905. The guy behind this world-changing idea is a young clerk at the Swiss Patent Office in Bern. His name? Albert Einstein. So while he's sitting at his desk looking over other people's inventions all day, he was quietly piecing together a revolution in physics. And this was the bombshell question right at the heart of his paper. You have to understand, for more than 100 years, everyone knew light was a wave, right? Flowing all smooth like ripples in a pond. But Einstein comes along and asks, hey, what if all of that is wrong? What if light is chunky? What if it actually comes in these tiny, discrete packets of energy? Kind of like a spray of microscopic bullets. Today, of course, we call them photons, but back then that idea was, wow, it was pretty much heresy.
Now look, this wasn't just some random thought he had. Einstein was basically being a detective. He was investigating a series of clues, these unsolved cases that were giving physicists everywhere a major headache. The beautiful, elegant theories of the 19th century were starting to show some serious cracks.
So on one side, you had the reigning champion, the wave theory of light. And it was awesome. I mean, it perfectly explained how light reflects and bends and all that good stuff. But on the other side, these new experimental puzzles were just stubbornly refusing to play by the rules. Things like why hot objects glow a certain way. That's blackbody radiation. And this really bizarre thing called the photoelectric effect. The master key that had unlocked so much of physics had suddenly just stopped working.
So, what does Einstein do? He proposes what he called a heuristic point of view, and this is so key. He wasn't standing up and saying, I have the final truth. Not at all. He was basically saying, hey guys, let's try on a new pair of glasses. Let's just use this as a tool and see if the problem makes more sense. It's a way of thinking that's at the heart of huge scientific breakthroughs even today.
And here he is in his own words from that paper. Just listen to how carefully he is, almost humble. It seems to me are more readily understood if one assumes he's not shouting from the rooftops. He's just inviting everyone into a thought experiment. He's saying, look, let's just pretend for a minute that light energy isn't smooth, that it's all clumpy and parceled out. Let's just follow that idea and see where it takes us.
And to back up this completely audacious idea, he pulls out this totally unexpected and, frankly, brilliant analogy. He found a mathematical clue that showed that, under certain conditions, light behaves exactly like a simple gas. Yeah, you heard that right, a gas.
Now to follow his logic, we just need to quickly get one concept down: entropy. Don't let the word scare you, it's pretty simple. Entropy is just a way to measure disorder or randomness. Think of it like this: a brand new deck of cards, all sorted by suit and number, has super low entropy. But if you shuffle that deck, well, now it has really high entropy, because the cards can be in millions of different random arrangements. Okay, so Einstein sets up this brilliant comparison. Physicists already knew the equation for the entropy of a gas in a box. It all depended on the number of separate, independent gas molecules bouncing around in there. So then Einstein asked the big question, okay, what about the entropy of light radiation in a box? What does the math tell us its disorder depends on?
And this, right here, this is the smoking gun of the whole paper. On the left, you've got the equation for the entropy of a gas. See that N? That's the number of particles. Now look at the right, the equation for radiation. You don't have to be a math genius to see this. The form of the equations is identical. It's a perfect match. Where the gas equation has N for the number of particles, the radiation equation has a term related to its energy. The math was practically screaming the answer at him. If the equation for the disorder of light looks exactly like the equation for the disorder of a gas, then light must also be made of independent, separate things, just like a gas is made of particles. The radiation was acting as if its total energy was chopped up into a bunch of individual energy quanta. This was a huge philosophical leap from a smooth, continuous universe to a grainy, quantized one.
And just like that, with this incredibly powerful piece of reasoning, the culprit in our scientific mystery was revealed. The energy quantum was born. And it didn't come from some direct observation, but from this profound mathematical analogy.
So let's put a pin in it. What is an energy quantum? Well, it's the smallest possible unit of light energy you can have at a certain frequency. You can't have half a quantum, it's an all or nothing deal. It's a single packet, and its energy is tied directly to its frequency, basically its color. So a quantum of high-frequency ultraviolet light is a high-energy bullet, while a quantum of low-frequency red light is a lower-energy one.
Okay, so Einstein's got this remarkable, totally radical idea. But look, a theory is only as good as the problems it can actually solve. The real test was about to begin. Could he take this new concept of the light quantum and throw it at those unsolved mysteries that had completely stumped the old wave theory?
Let's focus on the big one, the photoelectric effect. Remember, this was that really bizarre observation where shining light on a piece of metal could kick out electrons. But the way it happened made zero sense if light was a wave. So, could Einstein's new energy bullet model finally crack the case?
When you think about it this way, the whole process is just beautifully simple. Step 1, a single light quantum, one energy bullet comes flying in. Step 2, it slams into one single electron and transfers its entire energy packet all at once. Step 3, the electron uses some of that energy just to break free from the metal. And step 4, whatever energy is left over, well, that becomes the electron's speed. Simple as that.
And this simple model, it explained every single confusing part of the experiment perfectly. Why did you need high-frequency light? Because you need one single quantum with enough oomph to knock an electron out. A million low-energy quanta won't do the trick. Why was there no time delay? Because the energy transfer happens in an instant. It's a collision. And why did brighter light release more electrons but not faster ones? Well, brighter light just means more energy bullets are hitting the metal every second, causing more collisions. But the energy of each individual bullet stays exactly the same. Boom. The case was cracked.
So what started out as Einstein's very cautious heuristic view ended up becoming one of the most profound and consequential ideas in the entire history of science. I mean, its legacy it's almost impossible to overstate.
After he proposed it in 1905, people were deeply skeptical for years. But then, by 1915, these incredibly careful experiments by Robert Millikan confirmed Einstein's predictions perfectly. In 1921, Einstein got the Nobel Prize, and not for relativity, but specifically for this discovery. And then, finally, in 1926, his energy quantum got the cool name we all use today, the photon.
So, Einstein's heuristic view became the very foundation of quantum mechanics, the science that powers pretty much our entire modern world. And it leaves us with this really fascinating question to chew on. What are the strange, heuristic ideas that scientists are debating today that are just waiting for their moment to rewrite our reality all over again?